All right, welcome everyone. All 6 of you. I think one of the current viewers are little. I see 7 concurrent viewers, but I think one of those is me. So, just as a reminder, if any of you guys know anyone who's not in here, yell at them and tell them to come to class in online here. Because if we don't have people asking questions, then there's no review, right? Like people need to be in here to ask questions, otherwise they're just gonna be staring at nothing for 50 minutes. So I realized no one came to my, plenty of people came to my noon 3A lecture, but no one came to my no one came to my my 2 p.m. So it's kind of pointless if no one's there. I'm gonna put this pause screen up so my kid can get out of the way. Thank you. All right. Next step is to get a green screen. Anyway, so yeah, so feel free to ask me questions about your exam. I have gone through, awesome, thank you. I've gone through some of your submissions. I think anyone who submitted the practice scanning assignment, I have gone through it and graded it and made some comments. So just as a couple of things I want to note that I'm seeing, a lot of you need to write darker. So if I wrote that, probably the easiest thing to do is you get a pen, okay? Remember, you can just cross it out and throw away that sheet of paper if you need to, you know, or you can just cross it out anyway and just write. I mean, it doesn't really matter that much. But I would use a pen if you're having trouble writing it all, because here's the thing: there's not going to be any second chances. Your exam is the thing you submit to me. If in the end I can't read it, then I can only grade what I can read, right? So you should make sure it's dark enough. Some of you might want to write a little bit bigger. Some of you might want to avoid lined paper. It's kind of okay, but honestly, it shows up and looks kind of hard to read. I don't know. It's actually fine for the most part, but I would try to avoid it if you can at all. Second, some of you, I basically am looking at what is a picture of a piece of paper instead of a scan. So use Dropbox. Okay, I made a video for you guys just for you so that you could see how to use Dropbox to scan things. So please use that. If I made a comment like any of these sorts of things, please correct those things. I want to have perfect, you know, I don't want to have any trouble. I don't want to feel bad because I mark you off because I can't read what it's saying or it's annoying to read it. So, you know, do that. Anyway, any questions? I have my whiteboard right here. That way I get a point. My whiteboard right there, you should be able to see. So we can write on there and it should show up. So if you have questions, feel free to ask. How do you find all of the distinct equivalence classes of a given equivalence relation? Okay, well, that is a very, very open question. You kind of have to just see, well, I mean, so it depends, right? It's like, what is it if it's congruency? I mean, I'm assuming that you can probably figure it out for congruency, but for other stuff, it just kind of depends on what it is, right? Like, you have to usually set up some kind of equation between the two things you're finding equivalence of and, like, solve it. So, for instance, like, some of the homework problems, right, are like, you know, just to give you an example, I want to say this is a problem I saw. Someone asked me, Sullivan, you do have to submit to Gradescope. I've already seen yours, for instance, and write darker is all I'll say. But like, no, you're fine. If you submit to Gradescope, it's fine. Like, for instance, I want to say that there was something like X, Y, or maybe it was this. Sorry, hold on. What was it? X is congruent to Y if and or X is equivalent to Y if and only X, Y equals a constant, right? So like, how do you find the equivalence classes to that? Well, I mean, so what is the equivalence class of X? Is that an equivalence relation? No, it's not an equivalence relation. So, Troy, basically to answer your question is, I mean, if you have a specific example you want to see, like that you're thinking about, feel free to ask. But it's a very wide open question. But basically, you know, you have to just say, okay, well, what are the equivalence class? Set up that equation, figure out, solve it, and see if you can find a relationship between the two elements that are equivalent, right? I don't know. I'd be happy to answer a question if you have a particular example you'd like me to go over. But otherwise, I'm not sure. Shamwei, what is the method to prove well-defined from one set to the other set? Again, these questions are vague. Like, you're trying to give me questions. You guys gotta give me more specific questions here. That's really vague. So, like, in general, right, if you have a function from like, say, some set modulo an equivalence relation to a set A, right, it's well defined if you have two elements of X modulo that equivalence relation. So what are the elements of this thing, right? They are equivalence classes. So if you have two different, so remember, let's talk about this for a second here. If you have this thing, right? This is the set of equivalence classes of what are equivalence classes? They are sets of elements in X where everything in that set is equivalent by that equivalence relation. So in this case, when I write down the equivalence class of X equals the equivalence class of Y, I'm sort of writing, the assumption I'm writing here is that X and Y are separate elements of X, but they are equivalent under the equivalence relation. So when I write the equivalence class of X equals the equivalence class of Y, I'm saying, okay, suppose you have two different ways of writing the same equivalence class. And you have to show that F of the equivalence class of X let me write that if it's well defined if the two equivalence classes are the same, then F of the equivalence class of X will equal F of the equivalence class of Y. And it doesn't really matter which of the two elements you pick. That's it. Okay. In terms of a function to be well defined, why all questions so far is about congruency? I don't know. Why are they all about congruency? I mean, because mostly when we talk about congruency and well-defined functions, we tend to just deal with Zn. That's a lot of our interesting ones that we're interested in. I don't know. Can you say it's well-defined? I don't know. You tell me, man. Figure it out. Go through the proof real quick, and then see if you come up with a problem. How do I prove an interval is denumerable? So for intervals, what I would do to prove an interval is denumerable is you already know that the interval from 0 to 1, or if you want the interval from 0 to 1 open, both of these are denumerable. Or, no, I'm sorry, what? An interval is not denumerable. You trying to show it's an interval is not denumerable? Yinan, come back on that one, okay? An interval, sorry, my brain was, I hate the word denumerable. It sounds like not enumerable, which is basically what I would call uncountable. So, intervals are uncountable. So if you want to ask me how to prove an interval is uncountable, feel free to put that in the chat, but I'll get back to you on that one, okay? All right, can you please talk about question 2 of chapter 8 on the homework? What's the homework? The last one, homework 7? Give me guys, if you want a specific problem in the book, give me it like 8.1.2 or whatever. Give me the actual exercise number. That's more helpful than saying this thing in the book, okay? Because I don't have the homework open. I gotta find the homework now on my computer here. Yeah, like question 8.2.2. Okay, yeah, see, I couldn't have figured that out unless you tell me that. There's no way for me to know what you meant there, right? All right, 8.2.2. Let me find it. Okay, it says, suppose that G is a set from the 1, 2, 3, 4 to the power set of 1, 2, 3, and 4. And g of 1 is 1, 2, and 3. G of 2 is 1 and 4. G of 3 is the empty set, and G of 4 is 2, 4. It says compute the set A so that A is not in G of A. So again, oops, okay. Well, so G of 1 is 1, 2, 3. So that means that 1 is in G of 1. G of 2 is 1, 4. So so 2 is not in G of 2. G of 3 is empty, so obviously 3 is not in G of 3. Okay. And G of 4 is 2 and 4, so it is in G of 4. Okay. So if you're looking for that set X, X would be the elements 1 and 4. So from that problem. So this is 8.2.2 if you're just looking at this. Okay. Or no, sorry. It's 1 and 4. Okay. So it's 1 and 4 only. In part B, it says repeat it for G from n to its power set that sends n. Ugh. So what is that? It's all multiples of. Why is 1 true? What do you mean true? I don't understand what you mean by true in this case. Like, why is 1 in G of 1? Because G of 1 is the set 1, 2, 3, right? So it's just the element 1 is in. Yeah, because 1 is in G of 1, right? Oh, I'm sorry. It's not in. Okay. So, sorry. The complement of x. Let's just say a minus x would be 1, 4. X would be 2, 3. Sorry. Good call. Yeah, that's all. Sorry, I just x is the set of all elements in A that are not in their image. So, again, if you don't have it written down, I'm trying to not write down everything, but it's x in the set. Let's just call A the set 1, 2, 3, 4 here. Okay, so it's x in A such that G of x is not in G of x. Okay, sorry, I'm doing a bad job writing these things down right now. I'm going to add a new slide here. For part B, it says repeat it for. So for B, it says, yeah, x should be 2 and 3. From the natural numbers to the power set of the natural numbers, and G of n is the set of all x in 2n such that x is less than or equal to n. So look at what it's doing, right? It's just sending it to all of the multiples of 2 that are less than or equal to n. So n is going to be, so again, x is going to be all of the x in the natural numbers such that G of x, or sorry, such that x is not in G of x. Okay, so if you take an odd number, it's automatically not going to be, sorry, that should be a not in. So if say an element A is odd, then A is in X, right? Because every image is a collection of even numbers, right? It's all X in 2n. 2n is all of the even natural numbers here. So what is 2n? It's 2, 4, 6, 8. That's it. So if you have an odd number, it's automatically not going to be in its own image. Okay, so g of a will be all of the even numbers less than or equal to a. So if g is even, right? What does it mean if g is even? Or sorry, what if you have an even number? If b is even, is b in x? So someone from the chat, answer that for me, okay? How many people think yes? How many people think no? Feel free to just type in the chat. No one? Yeah, it's not. Yeah, so you're right. It's not in x. Or sorry, let me just say no. Because, right? It's just if g of b is all even numbers less than or equal to b, well, if b is even, then b is an even number less than or equal to b. So you're good. So that's it. So x is just all the odd numbers. Okay. So that's 8.2.2. So hopefully that helps. Let me go back up and find how to prove. Okay, so someone said how to prove an interval is denumerable. Again, sorry, I'm back on that again. If you want to say uncountable, let me know. Otherwise, I'm going to assume that intervals are not denumerable, so you can't prove it, right? All right. So David, is it sufficient to say set A on R is not denumerable because we have? I don't understand the question. I'm sorry. What do you mean a set A? A set A subset of the real numbers is not denumerable because we have 0, 1, and other sets form a partition of that set A. I'm sorry, I don't understand. So generally speaking, if you want to show that a set of real numbers is not denumerable, okay, or if you want to show a set of real numbers is uncountable, usually the easiest way to do this, if A is a subset of R, if we want to prove that A is uncountable, so I would use uncountable. So Jin, I have posted the odd and the odd problems from chapter 7 and 8. I'm not going to post the even ones because now that your exam is effectively at home, I want to have some problems that I can rely on that that you don't have solutions to. So sorry, I'm not going to post the even number ones. If we were doing this, if this was a normal year and there was not a pandemic, I would have given you the chapter 7 and 8 problems, but I feel like I need to have some problems that I can just throw in there that you don't have solutions to. If I give you guys book problems now from the first 6 chapters, you guys have all the solutions to them, which means now from chapters 2 through 6, I have to write my own problems now, which is a pain. So, yeah, so if you check the file section, 7 and 8, the odd problems are already there, but I'm not going to post all of them. Okay, sorry. Yeah, so if you want to prove that A is uncountable, just find an injection f from the interval from 0 to 1 to A. So if you have a subset of real numbers and you want to show that that subset is uncountable, which if you say not denumerable, you shouldn't say that, you should say uncountable, because here's the thing, technically not denumerable could mean uncountable or finite. So those are two really different things, right? So I would just say uncountable if you want to show it's uncountable. Or if you want to say it has a cardinality larger than the natural numbers, say uncountable. Anyway, Yeah, just find an injection. So, for instance, you said if you want to show that negative 1 to 5 is uncountable, all you got to do is just find any injection. So, for instance, negative 1 to 5 is a subset of, or sorry, other way around, my mistake. The interval from 0 to 1 is a subset from negative 1 to 5. So just let f from 0, 1 to the interval negative 1 to 5 be given by f of x equals x. Now, it won't always be this easy, but that right there is an injection. Can we say that that forms a partition and 0 to 1? I mean, yeah, basically, if a set, here's the thing. If A is a subset of B, or sorry, so this is a theorem, right? This someone go look in your book and someone tell me this should have been a theorem in the first section on set theory we did. That says if A is a subset of B, then the cardinality of A is less than or equal to the cardinality of B, right? That's a theorem from chapter 3. Chapter 3. I believe... Did we do cardinalities there? No? Well, maybe we never did. But here's the thing. The proof of this theorem is really straightforward, and it works for infinite sets as well as finite sets. So what is the proof? Let f from A to B be given by f of A equals A, then f is injective, and we're done. Sorry, I realize I'm writing into my, I don't know if you get, I have the hang of not writing into my, the webcam box there. So basically, if you have subsets, right, if A is a subset of B, the injection you can use is just the identity function, right? Just map every element to itself. That will be an injection automatically. You don't have to prove it. It's straightforward. And that tells me that the cardinality of any subset has to be less than the cardinality of its superset. So if you want to show, for instance, like I said, this interval from negative 1 to 5 is uncountable, well, it already has to have a cardinality at least as big as the cardinality of 0, 1. Okay? Yeah, so you can definitely say that. So if A is a subset of B and B is denumerable, you can... Do you mean uncountable? So if A is a subset of B and B is denumerable, all you can say about A is that its cardinality is less than or equal to that of the natural numbers. So remember, denumerable means having the same cardinality as the natural numbers. So if A is a subset of B and B has the cardinality of the natural numbers, that means A is either finite or has cardinality the same as the natural numbers. So you can't say that A is denumerable because you could say A could be finite, right? But it could be finite or countable. Or rather, I should say it's countable. So I don't know if our book uses the word countable. You can, generally speaking, you can use the word countable to mean finite or denumerable. And then anything that's not one of those two things is uncountable. Okay? Does that make sense? I know that the terminology around all of this is weird, and it probably doesn't help that the word denumerable makes my brain hurt because to me denumerable makes me think uncountable, but denumerable just means denumerable is countably infinite. Okay? how to show that there is an infinite number of rational numbers in any interval, no matter how small the interval is. Okay, well, suppose that there are. Do it by contradiction, Jashin. Do it by contradiction. Let Q and R be in your interval I, right? And suppose, or let me rephrase that. Sorry. Let me be more precise here. Suppose your interval has only. Okay. Sorry. So the question I want to answer is, let's show that in any interval there are an infinite number of rational numbers. So do this by contradiction. Suppose an interval I has n rational numbers, Q1, Q2 through Qn, and let's say that they're in order. Let's say that they're labeled so that Q1 is the smallest, Q2 is bigger, right? That's less than Q3, and so on. Okay? Can you see a way that we can get another natural number? Or another rational number? Can anyone see it? If I only have this many, right? How can I get another? So these should be all of the rational numbers. You don't see it? Okay, I mean, just do this. Watch. Pick any two consecutive ones, right? Let's let x be Q1 plus Q2 over 2. Yeah, exactly. Perfect, David. Yeah, you got it exactly. So you actually want, Gabriel, you want the sum. You want the sum. Because if you add them up, this is the element, this is the midpoint. This is the midpoint of Q1 and Q2. So what that means is that x has to be between Q1 and Q2. X clearly has to be a rational number, right? Like if it's an average of. No, you don't need the sign. It's fine. Q1 plus Q2 over 2 is just the number in between Q1 and Q2, no matter what Q1 and Q2 are. Right? It's just the average of the two of them. That's it. So if Q1 and Q2 are in the interval, x will of course be a rational number because it's just going to be, the sum is a rational number, and then half that is still rational. It's going to be a rational number, and it will be in the interval. So if you could only have a finite number of rational numbers, if you only had n rational numbers, then you can find another one, which doesn't make any sense if you have only n, right? So that's it. So there's your contradiction. That's it. Okay. Troy, probably not in that case. I mean, I'm not going to give you a theorem that's proven in the book. Seems kind of pointless, right? For me to give you something like that, since it's going to be open book. So your exam. So just FYI, guys, about your final exam. So basically, my only concern is that you can't use anybody else. So you can't go on the internet and ask the Stack Exchange. You can't do the problems with anyone else in the class. I'm gonna check, and I have an idea for how to verify this. I'm not gonna tell you what it is because then you might be able to defeat my plan here. But I have a way, I think, of checking to see if you guys have the same, if you guys are copying off one another, or whatever. So That being said, there's no way I have to restrict you from using the book or notes or anything like that. So I have no way of doing it. So I'm just going to make it open notes, open book. So you can use your book, you can use the notes in class, you can go back and watch another lecture if you want. Um, um, that's it. But yeah, so if to go back to your question, Troy, if there's no canonical map problems, then I can't really give you a proof of something that's in the book, right? Joshin, I think, yeah, you're right. So that's the only part of my proof that actually I didn't address is what if you have an interval where there's only, and an interval where there's only one, um, one, like what if you can't assume that there's n? What if you can only assume that there's one, right? I don't know how many problems there are going to be. So I don't know the answer to that question yet. So David, I don't know the answer. I don't know how many problems there will be. I have not written it yet. I know I'm sort of behind, but I've been doing a lot of effort to try to get all my stuff online and have all of this ready to go. I basically set all this up in the last like 48 hours. So I had like a way to stream before, but I've been trying to do a really good job here. So yeah, so I don't know. Sorry, I have not written it. Oh, but yeah, Josh, so yeah, you should prove that there's at least two, right? But I mean, like, think about it this way. All you have to do is say if you have an interval from A to B. So if you have an infinite interval, like if you had like A to infinity, well, clearly if you have at least one rational number in that interval, then then you can just say, okay, if it was an infinite interval, just add or subtract 1 to it, and that will have to be in the interval as well. So if it's a finite interval, then the difference between A and B has to be equal to something, right? So it has to be a positive number. So there exists, if your interval is A to B, then there exists a natural number n such that the interval of A, the length of that interval will be strictly bigger than 1 over n, right? So whatever the length of that interval is, you can always find such a natural number. And so if Q is in your, if Q was in your set, just you can just sort of say, okay, well then there's another rational number in there because you can just make it small enough, right? So it's not a very interesting proof. There's a lot of details there, but basically you have to just say, okay, cut up the interval into, halves, and then either, Q minus 1 over n over 2 or Q plus 1 over n over 2 would have to be in there, right? So anyway, other questions? I don't know. Are solutions to all the problems up on math? Are they on Chegg? Has anyone looked? Like only UCI uses this book, right? So if someone someone from UCI would have to like put stuff on Chegg for this stuff. The other thing is if I find out someone has a solution on Chegg, then that they will uh, they will be caught cheating basically, right? So if I have to get a subscription to Chegg, I'm sure the math department will subscribe, will pay for one. I mean, it has solutions. It doesn't mean you're gonna be able to find it, right? Doesn't Chegg work better if you have um, yeah, so I'm looking at Chegg right now, and I just Googled it with Neil Donaldson, who wrote our book, and someone asked for help, I guess, but some people answered. I'm assuming that you're probably not going to be able to get answers right away. I don't know. I feel like it's a kind of a Hail Mary for Chegg to show up on Chegg. I don't think it's going to be a thing that I should be too worried about, but, you know, if I have to pay for a Chegg subscription to catch cheaters, then I will. Gabriel, let's see. The textbook uses Cantor's diagonal argument for 0, 1, and I have seen other books use the argument for 0, 1. Nope, doesn't matter. Here's the thing. If you think about the argument that we used, to do this problem, going back to our proof of it, we basically constructed a number C that was in the interval from 0 to 1 that was going to only have in its decimal expansion 1s and 2s. So the thing is, if your number in your decimal expansion only has 1s and 2s, it can't be 0 or 1, right? Because the only way to get 0 with a decimal expansion would be your decimal expansion is 100% zeros, and the only way to get 1 with the decimal expansion would be to have all 9s. So since our decimal expansion of that element C we constructed is only 1s and 2s, it's already in 0, 1. So that's it. That argument works either way. Because all that argument is doing is showing that there's no bijection. Basically, it says that there can't be a bijection. It shows that there can't be a bijection. It assumes that there can't be a bijection from the natural numbers to the set to the interval 0, 1, but the fact that it's open or closed makes no difference. Okay. Nelly, are you here? I'm sorry. I don't know why. I kind of have to use an automated moderator. I just don't want to have, obviously it'd be very bad for my career if someone showed up and started swearing. I don't know why. It seems to have a trigger finger. I have no idea what word that you posted there had a problem. I don't see anything. Yeah, any interval is automatically uncountable. Yeah, sorry about that, Nelly. I don't know what happened there. But you can. So the proof that any interval is uncountable is pretty straightforward, right? Because if you have an interval, say just A to B, let's see. So suppose you have an interval A to B and you wanted to show, we can actually generalize. I can just show you literally all of them at once, right? You have an interval A to B. Let's take the difference. I guess I could just do B minus A and call that L just for the length of the interval. Then you can just scale, take F from the interval, say 0, 1, or even the open interval 0, 1, doesn't really matter, to the interval from A to B. I don't know, just to do it perfectly, you could just say let f of x just be x over 2L. So that's going to map. So if I sent x to x over 2L, then the map sends the interval from 0, 1 to 0 to 1 over 2L. So it shrinks the interval length by half of whatever the interval length from A to B is. and then just add to it a plus 1 over 4L, and that will do it, right? So this thing right here, that is a bijection, or sorry, that is an injection from the interval 0, 1 to the interval AB, for instance. So there you go. So that shows that any interval from A to B is uncountable. Okay. Troy, yep, you sure can. So if you have a collection of sets, you can just say, if you have a collection of sets, let's say X is equivalent to Y if and only if they're in the same element in that set, in that collection of sets, then if you show its equivalence relation, then yes, that's all you have to do. 7.4.1, by defining an equivalence relation, show that they partition R2. Let me take a look here. 7.4.1. Okay. By the way, if you're in chat right now, if you're watching this, please do the scanning assignment. I actually went through and graded people who had submitted. I think we were at like 19 people, which is pretty good actually. I think a lot of people had done it already. I made comments. I don't think I published your classes yet. I will publish your class. Maybe I did. I don't remember. I will publish it right now. So it should publish. Let's review grades. So there are a couple people who've done it recently who haven't submitted yet, but I published the grades. I should be able to go back and grade the people who haven't had theirs graded yet. But for like 19 of you, I published the grades. So go in and read the comments, okay? Like some of you guys just was too light or you didn't do a good job scanning it. So try to fix the things that went wrong, okay? All right, sorry, back to math here. Okay, so sorry, Troy. Let's go back to find that real fast here. So we wanted 7.4.1. Okay, let's see. So for each of the collections, determine if they are a partition for your answers. Yes, so yeah, you can exactly do that. Yeah, so if you can just say, okay, so let's have a look. So let me just try part A right here, right? So for 7.4.1a, you can define an equivalence relation. X is equivalent to Y if and only if, X is equivalent to Y is X, so the ordered pair XY is equivalent to the ordered pair AB if and only if XY and AB are in the same AN or if only if there exists a N such that they're both in AN. Okay, so you're saying you want to sort of define equivalence relation like that and show that if it's an equivalence relation, then it has to be a partition by that theorem, right? That says that if you have an equivalence relation, then the equivalence classes partition the whatever set X that they're on. So to do that, right? So you could think of, XY is in AN if and only if Y minus 2X equals N. And so XY is equivalent to AB. So even if they're in the same AN, which is the same as saying that Y minus 2X equals B minus 2A. And so you can check, like, is that an equivalence relation? And the answer is yes, right? So this is an equivalence relation. Which implies that the collection AN for N in the real numbers partitions R2. So Troy, I don't know if that made sense, but I think that's what you're asking, right? Basically, you can just try to figure out is the relation, those two ordered pairs are related if and only if they lie in the same AN. If you can show that's an equivalence relation, then that automatically shows it's a partition, right? I'd rather not see pictures. Pictures aren't proofs. That being said, you should. So no. So no. Pictures aren't proofs. So don't give me a picture to show what it is. You should show me if you want to do that problem directly. The problem I just did. If you want to do it directly, you should. Sorry, sort of move this out of the way here. You should show me that that AN and AM. If you have an AN and an AM, you should show me that they're disjoint, right? For when N and M are different. So basically, this shouldn't be hard to do for instance, for part A, but show that any two of those elements in that collection are disjoint if they're distinct elements. And then, show me that every ordered pair in R2 is in one of them. That's not a drawing. That's me setting up a function. That's just you understanding how it works, right? It's not a drawing. I drew it, but that's only to explain how to write the function. So it's more of a visual aid than a proof. Okay. No, for those problems though, don't just draw pictures. You got to show me. You got to either do what I said before, which is show that the relation X that two ordered pairs are related if and only if they're in the same set in the collection, or do it directly. Show that any two elements of the collection are disjoint and that they together, their union will give you the whole thing. Okay? Any other questions? So time's almost up here. So yeah, just as a reminder again, so be in front of your computer at, I believe, 4 p.m., right? So at 4 p.m., the exam starts. I'm going to post it to Canvas. You're going to need a bunch of blank sheets of paper. So however many problems... Oh, Nelly, yes. So the grading scale is going to change. I'll make a Canvas post. I will possibly subscribe to Chegg, yes. Do I have Canvas open here? Yes, I do. Okay. So yeah, so the math department has suggested that we reconfigure the our grading scale so that it's not weighted as much on the final. Okay, so currently your grade is homework is 15%, quizzes are 15%, your midterm is 30%, and your final exam is 40%. I probably will drop the final exam to be 30%, and I'll probably put the other 5%, the other 10% into quizzes and probably the midterm exam. Maybe quizzes and homework then. Quizzes and homework will be an additional 5%. So the new scale will probably be 20% homework, 20% quizzes, 30% midterm, and 30% final. So the final won't be worth any more than the midterm. And apologies, but it's mostly just because, well, I'm giving you guys an at-home test now, so it's a little bit different than we normally would. So the math department told me to do this, so don't blame me. Sorry. I can't guarantee I will subscribe to Chegg, but I take cheating seriously, okay? So if you're getting stuff off the internet, I'm going to find out, all right? Any other questions? Okay, so be in front of your computer at 4 o'clock on Monday. I will post it to Canvas because I'll have 2 hours. So if for some reason there's any kind of delay, I'll obviously give you some extra time. But you'll have 2 hours to do it and 20 minutes to scan it. If I wrote that your scan looked bad, on the Gradescope thing, please just sign up for a Dropbox, guys, and just use Dropboxes. It's totally fine. Some of you guys look like you just took pictures of it. Like, I don't want to see your countertop in the background. Use some sort of utility that'll like clean it up, okay? I have to grade. It just makes it so much easier if I'm looking at something that's kind of uniform from person to person, okay? So please just do a good job scanning it so that I can grade these easier. Because grading is already not very fun. Okay. All right. Anyway, have a good one, guys. I'm going to end the stream now. So I will talk to you guys on... Oh, I'll set up a discussion probably in the Canvas page so that if you have questions during the exam, you can ask me and I will monitor it carefully. Okay? All right, guys. Have a good one.